Okay, here's class 26. I'm recording this in fall 20, even though we're not going to do this for class 26. I'm hoping that we can learn a little bit about the raindrop cycle counting method. So the motivation here and the purpose, the objective, is we might find ourselves with, up to now, we've had nice and smooth kinds of stresses. We've had a mid-range and an alternating. We also took a look at the Manson method and minor rule, so that we had, if we had that kind of scenario. But what if we have now all kinds of things taking place? We need to try to keep track of all of these things, right? So we just had a simple two-stage process when it came to Minor and Manson's method. Now we want to have one where there's a scatter, all over the place. And we want to be able to convert this into something that can be compatible with that, the only information we have, which is from a constant, completely reversed test. So we need to do an apples to apples thing. So what we do is we take a look, and if we can, try to identify a block of time history, and we turn it on its side. And then we pretend that rain is falling, like little raindrops. And so if a raindrop falls, well, first off, we take a look at the peaks and the valleys, and we number them. Now, I like to number the valleys as odd numbers and the peaks as even numbers, if possible. Sometimes I might reverse that, but I try to keep it consistent. And we take a look and see what happens if a raindrop, let's say, just starts at the first valley in this case. And by the way, these raindrops have rules to them. It's a little weird, but the raindrops have rules. Now, in real life, raindrops don't have rules, but these ones do. And so if rain is allowed to flow on the roof and drip down, except for some reason, magical reason, it can't get past a point if it encounters a valley that has a larger magnitude or is more negative than the original one. So if you start at 1 and you start looking down, you'll see that 3 isn't as low, 5 isn't as low, 7 isn't as low, but 9 is lower than 1. So that first raindrop has to stop at 9. Right? So the second rule is if it initiates at a peak, the same dealio, right? In this case, it's going to start at 2, and if it encounters something that's larger than 2, larger than its peak, which is true at 4, it has to stop. And now, another weird rule is if the rain runs into the path of a previous If a raindrop runs into the path of a previous raindrop, it has to stop above, right? So here, take a look at 3. It runs into the raindrop's path of 1. Take a look at 5. Same thing. Take a look at 7. Can't go any further. And if you go through all the way right there, if you go through all of this process and you follow those rules, and sometimes they're tricky, sometimes it's hard to figure out, so you have to really meticulously come through there. What you're able to do is you're able to count and add all of these up together. So it's a strange sort of process, and doing it by hand is always a little weird. So it really does lend itself much better to having a computer algorithm to go run and do all this work for you, right? So here is just a run through narrated of the thing. 1 drops all the way down, just like we saw. It stops at 9. 2 stops at 4. 3 stops because of the raindrop 1. 4 stops at 6 because 6 is larger than 4. 5 stops here because it runs into a raindrop. 6 stops at 8 because 8 is larger than 6. 7 stops right there because it runs into a raindrop. 8 goes all the way to the bottom because 8 is larger than 18 and 26. So it can go all the way down. And the same thing, 9 has to stop at 13 because 13 is more negative, larger magnitude. 10 has to stop because it runs into the raindrop. 11 has to stop because 13 is bigger than 11. So you start to get the idea. And I think there's actually a mistake in here somewhere. Quite often some students who are really paying attention are able to find it. So anyway, this is the rain flow method. Now, the thing that you want to do after that is to isolate that. Okay, so we isolated the block. So we already did this step. Isolated the block. We performed the rain flow counting. Now the next step is to create a table and track the raindrop number. And here we go, number of cycles, but that's usually going to be half cycles. Every raindrop is really half of a cycle. And then, but we might see that its minimum and maximum might be the same as another raindrop. So that counts as an extra raindrops into that category. We want to be on the lookout for that. Now we figure out from that maximum, the minimum and the maximum, we find the alternating and the mid-range stresses. We convert that to, we convert everything that's a non-zero mean stress. We convert that into equivalent completely reversed stresses, right? And then we determine the fatigue damage fraction in each cycle associated with that completely reversed thing, right? So we employ Miner's method here, right? So there the Miner linear damage fraction, and then we use it backwards to estimate the remaining life, right? So it's a convoluted, complex thing, and it's really best seen through an example. And even better is to do it yourself, right? Quite often what you need to do as part of this right here is to do it in a multiple setting. So the raindrop method that I would employ here, I would identify a block as starting here and ending right there, right? And we note that if we look very carefully, this is going to be 1 minute long, right? You could even see from here to here, that's 1 minute of length. So that's kind of an important thing to look for. 1 minute long takes place here. And I number this, I'm going to go valleys here. 1, 2, and I'm going to be careful of my numbering so I don't get in the way of the raindrops. 1, 2, 3, 4, 5, 6, 7, 8. Probably will get in the way of my raindrops. 9 and 10 right here. So if I take a look at my raindrops, and I'm going to try to mess around with the colors to keep it, and I take a look at 1, we can see that 1 drops down here, and we take a look at the valleys, and none of them, it's going to make it all the way down to the bottom right here. So once again, my numbers got in the way. I got to be careful there. Right. So now I want to try to maybe take a look at 2. 2 comes down, but it has to stop right here because 4 is larger than it. And then 3 has to stop right here because it runs into the drop. And then we take 4, it can come down. I think 4 can make it all the way down. Boom, yep, because nothing is larger than 4, so it gets all the way to the bottom. All right, and then guess we'll go with that guy. We take a look at 5. 5 comes down. 5 can keep going. 5 goes here, 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 but it has to stop because 9 is greater than it, or more negative than that. We take a look at 6. 6 gets to right here, I believe, right? Yeah, 6 has to stop. Let's go to other colors. Go to him. 7 gets stopped right here. 8, it can keep going, okay? Because 6 did not make it all the way down to 8. So 8 can keep going, but it gets stopped right there at the raindrop from 4. And let's go orange here. 9 can come down, and it makes it all the way down, but it does get stopped by what would be the next peak up. And then one more here. Yellow's no good. Let's go to green right there. And so 10 gets stopped right here. So now what we want to do is make a table out of this. I wanted to keep this on the same page, so I made like half a table. My table will actually extend to be this large right here, but I will do this to try to keep it on the same page. So what I do is I start out with raindrop number 1. Raindrop number 1, I won't fill in what the N is right here, right? So I want to keep going how many raindrops I have before I fill in the N. So, but I take a look at what the maximum is of 1. The maximum, it appears to me to be 1. It goes all the way from here, right? So we take a look at throughout its path. It's -50 is its minimum, and its maximum is 40. Right here. So I put maximum and minimum. I think actually it was easier to switch these around. So I went to minimum and maximum just because the way this thing's arranged. The minimum's over on the left, so it's just like a little easier. So I go -50 to 40. Then I take a look at raindrop 2, and I don't want to keep messing around with the color, so I'll just go black. 2 goes from a maximum of 20 to a minimum of -10. So that's raindrop 2, -10 to maximum of 20. I got that right? Yep. Take a look at raindrop 3, and it's going from that -10, but it's stopping right here. Oh, look at that. It's the same, -10 and 20. So it's 3 right there. Raindrop 3 has the same, so it gets counted along with 2. And in fact, that becomes 1 cycle, because each of these is half of a cycle. So let's see if there's any more that fall into that category. So we have 4. 4 comes from 40, and you can track it all the way down. It goes all the way down 40 to -50, which is actually up here. Okay, so we have yet another cycle of there, another half cycle. If we go from 5, right, so that's like right here, tracking 5 goes from 10 to 30, right? So back between 10 and 30. So that is not one that we have before, so we'll start it on new row. And, by the way, this says that it's 10 to 35. Let me double check. Oh, yeah, right there. Yep, halfway point. Sure, it got me, 10 to 35. And then 6, let's track him. He goes from 30 to, and he stops at 20. So is it 20? Yeah. So it's so that's a new line. We don't have those already. So it goes 20 and 30 is its minimum and its maximum. 7, that's this guy over here. He goes between 10 and 30. So actually, he's actually going between 20 and 30 as well, right? If you track between there. So there's another raindrop right here. And then 8. It goes from 35 to 10. Oh, up here, 8, 10 to 35. And then 9 goes from 0 to 30. We don't have that one yet. But if we take a look at 10, we'll see that that one too goes between 30 and 0. So that's right here. And now we're done with this. We can see that each of these is half a cycle, so we actually have a cycle of each. There's nothing that says that you have to have matching pairs. There's nothing to say that they're going to equal 1. They could be cycling back and forth between several of the things before we make a complete thing. But this is a minute worth of time, and it has done all of these things. But now we have to like assess these. So I rewrite all of them down. Oh, this is 4, 1. So you know, this is not something that you have to do if you put it on a separate piece of paper or you put it in the line below. But in order to fit it onto there so that you could have an explanation, I put it right in there. We go 1, 1, 1, 1, 1. And I decided to make this min, if you remember, and this one max. So I was putting there, I went negative 50, 40, negative 10, 20, 10, 35. I go 20, 30, 0, and 30, right? And so sigma m, okay, so we know how to do that, right? Sigma m is going to be max plus min divided by 2. In that case, it turns out to be negative 5, right? And then max minus min divided by 2, in this case, comes up to 45. The same thing true for all of these maxes and mins, right? We get like a 20 and a 5, and we get a 35 and 22.5, and we get a 30 and a 25, and here we get a 30 and a 15. Now, what we want to do is find the completely reverse equivalent stress, right? So we go the rev is equal to sigma A divided by 1 minus sigma M over SUT, right? Now the problem with this particular example, and maybe I should try to like change all these numbers, is that like eventually what I find is I cancel out a lot of them. So I really wish I had used a different material here. That really would have been helpful. But all of this information down here for this problem right here is provided, right? They already provided that the endurance strength was 20 and the ultimate strength was 62 on the thing. And from that, by the way, with 62, we could look up, we always find that that's going to be 0.9. So I really kind of want to change what this endurance strength is going to be. Because in this problem, like, in fact, I might make it, I might pause the video and change all of these things. I think 19 would be a better thing, because what I end up finding is from this, that I end up getting for the completely reverse stress, I get things that are below 20, and so I have to toss them out. So let me, I'm going to keep this, and I will pause the video and rewrite all the numbers. Okay, let me go back into this. So I've adjusted my values to make them something that would be maybe more useful for our purposes here. And so what I need to do for the completely reversed is to figure all these out. So what we end up finding, okay, so in this case right here, because this is negative, the mean doesn't matter if it's negative. We just use 45, right? We don't use this equation down below. But we do for this one, 16.3, and then this one is going to be 19.6. This is 8.38, and then this one is 19.8. You can see that the reason why I changed this from 20 to 19 is because we take a look and say the number of cycles to failure. In order to do that, we need to find this A and B, right? Which I've shown right here, which actually now they actually change to a new values because they are based on the endurance strength. So I have changed the A is now going to be 163.9, and the B is now negative 0.1560 right there. Okay, so I'm not going to write those up above, but I do plug them in for this N, you know, is going to be equal to sigma rev, you call it rev I maybe if you want to, divided by A raised to the 1 over B. And what I find, and I decided to put the actual numbers in here, 3,972 is my new value. 16.3 is less than 19, so the number of cycles are infinite. That's going to say being true for the 8.38. So those don't matter. Those raindrops don't matter. but this 19.6 is larger than my 19. That's the reason why I made it a lot more. So that's 813,000. I think that's a 900. And then also that 19.8, and that should be a pretty large number because it's close to our 19. Actually, it's closer. Yeah, okay, anyway. 770, 800, so 770,800. Now what I want to do is I want to take 1 over, right? So I'm going to take this n over this n, right? Which is essentially, in this case, because these are all 1 right here, so that's what that is right there. That's the damage fraction. I'm really taking the inverse of all these. So these are all going to be pretty small numbers. So I'm going to put them in scientific notation with a e to the -4. 1 over infinity is 0. This is 1.23 e minus 6. This is 0 again. And this is 1.30 e minus 6. And then I add them all up. All the di's that are involved right here. And it ends up being 2.5. I have an Excel. I'll show you the Excel here in a second. Maybe good. 2.543 e minus, where'd you go? E minus 4. Yep, that makes sense. And now, what I'm going to find is that I want to figure out the number of blocks, right? So remember that this was just one block that was taking place between here and here. It lasted 1 minute. So we want to figure out how many blocks. So I'm just going to call it capital B times the summation of di's to equal to 1. Remember, because that's what we were, the whole idea here in the minor's rule was going to be the damage fraction has to equal to 1. Well, how many of those fractions does it take, right? So this was actually pretty easy to do here. And so you say that it's going to be, I guess I'll go like this, B times 2.543 e minus 4 equal to 1. It's just taking the inverse of it. So we say that B is going to be 3,930 blocks of time. But in this case, each block is equal to 1 minute. So you go 1 minute per block times 3,930 blocks. And it equals to 3,930 minutes, right? Duh. 3,930 minutes, right? So divide that by 60, and then 60, and then the time estimated, maybe the time estimated how long this thing will live ends up to being 66 hours. And there you go. That's the big idea. It's like a predictive maintenance type of thing, or a predicted. Well, it is for maintenance. That's the idea behind it. Is that we want to try to estimate how long something is going to live. And I have a bunch of other examples, but I think this is the best example. Now it's a better example now that I reduced that thing to 19. So I'm going to discard those, and there you go.